the main thing that we're struggling with is using the actual groups to our advantage and working with them. Because from a bigger picture, abstract level, I feel like I have a general understanding of how things work. But when we start looking into the details of, I guess breaking down, for example, groups into their, I guess, irreducible representations, I guess a little tricky. So if you could kind of walk through, for example, we see all the different, I guess, titles for the different groups, like S3, C3, D3, and all these things.
How do we use the names? There are 3 families of classical groups, and then there are 7 exceptional groups. In this course, we don't care about exceptional groups, only classical groups. And they're defined by what they preserve as an invariant. If you want to preserve Euclidean length of the dimensional X transpose times X, where X is a vector with components 1, 2. Let's say it has n components. So this is just the sum over xi squared. So this is a, Pythagoras theorem definition of length squared. Then a group transformation is, in this case, just a matrix multiplying the vector, let's say R X, and R is any real n times n matrix. Then when we transpose it, we are looking at Rx transpose times X. And, when you transpose, you tell me whenever I have to explain something more detail, but when you transpose matrix acting on a vector, that's the same as X transpose of the matrix. So they reverse their order. Dot R X, which means we have X times matrix transpose times matrix equals X. So this is a column, this guy is a row. And this has to be true for any non-zero axis. The only way this can be true, only if the matrix transpose is the matrix inverse. Because when that happens, this is identity, and we find out that the length of the vector after transformation is the same as before. So that's now called orthogonal group because it preserves orthogonal coordinate frames. And the usual way to write it is to write orthogonal group in n dimensions. This representation has various names, but fundamental representation. Because it's not really true, but it's classically one thought that was the smallest the matrix that would represent orthogonal rotations that preserve lengths. And there is a little detail to it. This matrix could also be a matrix, the parity matrix. We think of this as rotation matrix, but it could also be a matrix when you take a point and you just change all its coordinates to minus themselves through the origin. So this is inversion through the origin. So this is nothing that you easily do with a physical object, because physical object you cannot really invert into themselves. But mathematically you can do it. And that group, orthogonal group, includes all the matrices, including these inversion matrices. But if you do the logical thing, which is you allow only rotating things smoothly without inverting them, then you get special orthogonal group in n dimensions, which has a property that the determinant of R is +1. So that's special orthogonal group. So that's how people think of classical groups. I'll define two more. I'll also have to define unitary and symplectic. And when you learn this, you think there's only one representation. Any matrix whose transpose is its inverse is allowed. Okay. There are infinitely many of them.
Whereas the special group is just one with that criteria that the determinant is 1.
Yeah, special is determinant 1. Now, it's easy to convince yourself that the determinant of this matrix has to be plus or minus 1, but it doesn't matter right here. But basically, the matrix, it should be any matrix, with any values of elements, such that it can be inverted, meaning it has no, zero eigenvalues if you try to diagonalize it, or if you compute its determinant. But not only that, determinant has to be 1. Continuous groups are always infinite. They have infinitely many elements because you can choose any set of real numbers such that determinant is +1 and that transpose is the inverse. There are infinitely many of them. So all continuous groups have infinitely many elements. And that's why we start defining, generators of infinitesimal transformations. Their number is finite, but the number of elements of the group is infinite. So that's the different thing from finite groups. For finite groups, we found few group elements, like 1 for translations on a circle, whose, as we raised it to power u, we found the whole group, and that was it. There was a finite number of group elements. We were done. And that number was called an order of the group. Now, that only makes sense for finite groups. And you can think of continuous groups, like rotation on a circle, as a limit in which you put many, many points, eventually infinitely many points on a circle. So the order of the group becomes infinite, if you think of it as a finite. The continuous groups, if you think of them stepping, in little steps, they are limit of a process where steps can be infinitesimally small.